so this is the cluster we're currently working on. It's a dense, high-performance embedded cluster built out of Texas Instrument Panda boards. Panda boards have the TI OMAP 4. In particular, our model, the early Panda boards have the 4430 OMAP on them. Each of the nodes runs at 1 gigahertz, has 2 cores and a gig of RAM. And we're running right now, we're running a benchmark, a scientific benchmark, just to see what kind of performance we can get. Later on, we have a couple of applications we're going to investigate to see if we can get some usable science out of this. We're going to look at a molecular dynamics program and some protein folding applications and see how well those run on the ARM architecture. The ARM architecture is substantially different than the conventional architectures, the x86, which is substantially what we use in scientific computing. But we built this cluster for a proof of concept experiment to determine a couple of things, both on what kind of high performance we can get out of it, and more particularly what kind of low power usage we can get out of it. And we'll compare both of those numbers. We'd like to get some reasonable performance out of it relative to the x86 similar model on the x86, and we'd like to certainly meter and document that we can repeat the low power experiments. So one or two of the power aspects we're looking into concern being able to have fine-grained control over the power usage of each individual Panda board. One thing you can do with the new software we're using is turn off individual cores when you're not using them. Alternately, you're allowed to change the speeds of individual cores. You can change them independently. The lowest speed we can run on our Panda boards is 300 megahertz. There's 2 other levels that we can run them at, and then full out at 1 gigahertz. So we're going to do some experiments by evaluating what kind of performance we can get done at the lowest speed and the top speed, and find out if that power level is worth the trade-off. We're also going to check and see whether or not turning nodes on and off in some capacity, either going into suspend RAM, which is suspend, or writing the state to the disk, which is hibernate, and then coming out of hibernate and recovering the state from where we were. We're going to experiment with those to see if they're worth the trade-off in time against power. We know that you'll use less power in suspend and hibernate. We just don't know if it'll be worth the time. It may be worth the time and power just to turn nodes on and off if boot times are low enough that they make sense to do it that way. The proof of concept demonstration to show what our low power usage is will be, we're going to take this outside and hook it up to solar panels to demonstrate that you can run this in a fairly low power, low energy environment. And we're doing that mostly to demonstrate that if you can run it off of solar panels in the middle of a field not connected to any power, that'll be our proof of how low power it is. Each Panda board we have consumes somewhere between 3 and 6 watts, closer to the 6 watts when we're full out at 1 gigahertz, running 100% of our math benchmark. And that appears to scale linearly. We're finding that we're able to scale up. Right now, I have my watts up meter. We're at 190 watts for the 48 Panda boards, plus the 7 USB hubs and the 48 port switch. Actually, no, we've taken the switch out of the equation. That's just for 48 Panda boards. So 200 watts divided by 50. We're tracking at about 4 watts right now, and that's with some percentage of them at 100% utilization, but most of them at closer to maybe 10% utilization. One thing we'll be testing with the watts up meter, with the power meter, is to see how much power we use when all 48 of them are at 1 gigahertz at 100% CPU utilization for 2 cores. And then, like I say, we'll test out some of the other options, turning off cores, throttling down the cores we aren't using, and we'll experiment with turning nodes on and off and see whether or not 100% utilization of 50% of the nodes is better than 50% utilization of 100% of the nodes. I think this would be good test to find out. And a 48 node cluster is a good place to do tests like that. We are going to be testing this for two purposes. We want to document and see if we can repeat the tests for the power management, and that's primarily for a poster that we're submitting to the IEEE Cluster Conference. This year it's in Beijing in September, and we're right on top of the deadline. So we're documenting that, and we're preparing that material for the paper. The other test we're doing this weekend, and what we'll do the solar power standalone test for, is to document that we can do a green 500 run, which is it's a very specific benchmark under very specific conditions. It's the high performance LINPACK benchmark, and we have to target it at double precision math. We've got a couple of algorithms that we'll test that on to make sure that we're compliant. And the one thing that we're doing differently, our special sauce this year, is running it off of solar panels. So we'll document the process and the procedures, and then we'll also capture the fact that we're running it off of our own generated power. Right now we're tracking individual performance per board at around 1 gigaflop double precision. We're looking to scale that up slightly superlinearly, so more than 48 gigaflops for 48 nodes, and slightly less than 200 watts for 48 nodes. So that's going to be about 0.25 gigaflops per watt, and that's a good ratio. That's a good green number. We hope to be able to document that this scales linearly or superlinearly in larger clusters as well. So one reason we put this together this way, we've overlapped Panda boards because we wanted to try to make this as dense as possible as part of our proof of concept demonstration. One thing you can do with Panda boards that you don't have the luxury of doing with some other single board computers is overlapping them and putting them in real tightly constrained environments, because your air cooling and your air conditioning requirements are much lower with the Panda board. We don't have any blowers or fans on this right now. If we closed it up and made it even denser, we'd want to put some fan or some blower system on it. But it's certainly a lot less. We don't need air conditioning. We would need at most fans, and we're going to experiment with that too. So this lends itself to a very dense cluster arrangement that you could stick under your desk or in a closet at work, and with only using 200 watts, you could run it off of house current. So one of our big research paths is investigating bringing some of the data the data and applications that people have now franchised out off-site because of the power usage and and scalability issues, bringing that back into your own data center or possibly into your office, because of now you've got a certain level of performance for a very reasonable power budget. So this could actually bring some of the applications that people have migrated up to cloud servers. They can now bring back down to their own office. And we think there is probably an opportunity here for what they call a missing middle, to bring some of these applications into the office and have the kind of control you have over a supercomputer or a cluster that's right on your premises.
So as Carl was explaining, this is a very low powered cluster of 48 Panda boards that consume less than 200 watts of power while being very high density. This is actually a trash can that was modified with the server switch and everything else. Very easy to build, but it's also fairly cost effective with a single Panda board. There's 48 of these in here, retailing for less than $200, and presumably in the coming months the price will drop lower as there's new ARM models that are being introduced, etc. And then actually setting up the software side of this is very easy as well. All these nodes are running Ubuntu 12.04 LTS, which of course is a very popular Linux distribution, and from there we're using a pretty much stock package set of the Linux 3.2 kernel, the MPI libraries as found in Ubuntu 12.04, and all the other software packages. So it was very easy to install Ubuntu, install the packages, mirror them across all 24 nodes, and from there you're going in a matter of a few hours. And yeah, it's very wonderful. So with the Panda board, you have basically 10100 Ethernet, dual USB 2.0 ports, HDMI, so you can drive up to HD displays on here. The graphics are backed by Power VR. They're good assuming the driver works out well. Audio and 5 volts. As Kurt was explaining, these boards consume between 3 and 6 watts depending upon the load factor. With the Panda board ES, which is the 1.2 gigahertz variant, I'm seeing roughly the same power consumption as well. Besides Ubuntu, Fedora has been enabling Linux support as well for ARM. Arch Linux, Gentoo, and all the other Linux distributions as well have all some concerted effort towards ARM, considering the growing market, just not in mobile devices, but going into servers, especially with next year's ARM server hardware, and then in desktops, notebooks, etc. Overall, the ARM Linux space is looking extremely exciting, and the best is yet to come in the next few years.